The effects of resistance of voltmeter and the resistance of ammeter on measurement. For an ideal ammeter, the internal resistance of the ammeter is equal to 0. In this circuit, the current passing through the resistor is I equal to V over R equal to 3 over 10, which is 0.3 ampere. If we put an ideal ammeter in series with the resistor to measure the current passing through the resistor, the current I will become V over R plus resistance of ammeter, which is equal to 3 over 10 plus 0. The current reading is equal to 0.3 ampere, which is the same as the actual current. That means the ammeter readings is exactly the same as the current passing through the resistor R. For an ideal voltmeter, the internal resistance of the voltmeter is infinite. In the circuit, the voltage across the resistor R can be found by using the ratio 3 times R over R plus R pi, which is equal to 3 times 10 over 10 plus 10, which is equal to 1.5 volt. When we put an ideal voltmeter across R in order to find the voltmeter readings, since the internal resistance of the voltmeter is infinite, that means there will be no currents passing through the voltmeter. Hence, the voltmeter reading will still be equal to 1.5 volt, which is the same as the voltage across resistor R. But for practical ammeter, the internal resistance of the ammeter will not be 0, but it will be very small. And for a practical voltmeter, the internal resistance in the voltmeter is not infinite, but is very large. In the circuit, the current passing through the resistor R is I equal to E over R. If we put a practical ammeter in series with R to measure the current, then the current read by the ammeter will be equal to E over resistance of the resistor R plus internal resistance of the ammeter. And since RA is very small but not 0, therefore we will get the ammeter reading I pi will be smaller than the actual current passing through the resistor R without the ammeter. And in this circuit, the voltage across resistor R1 is V1 equal to E times R1 over R1 plus R2. If we put a practical voltmeter across R1 in order to measure its voltage, the equivalent resistance across R1 would be equal to R1 times internal resistance of voltmeter over R1 plus internal resistance of voltmeter, which will be smaller than R1. In this case, the voltmeter reading V pi will be equal to EMF E times R equivalence over R equivalence plus R2, which is smaller than the actual voltage across R1. Let's see how to use ammeter and voltmeter to find the resistance of an unknown resistor when both the ammeter and the voltmeter are not ideal. In order to find the resistance of an unknown resistor by using ammeter and voltmeter method, if the resistor R has high resistance, that means when R is high, then we connect the ammeter and the voltmeter into the circuit by using this circuit diagram. The reason is that the ammeter reading I measures the true currents passing through the resistor R, which is again equal to I. And the voltmeter reading V measures the sum of the voltage across R, VR, and ammeter, VA. That means V equal to VR plus VA. And VR equal to IR, and VA equal to IRA. But since the resistance of R is very high and the internal resistance of the ammeter is very small, that means it's very low. Therefore, the voltmeter reading V approximately equal to the voltage across the resistor R. Hence, we can find the resistance of the resistor R by Ohm's law, which is equal to V over I, which is equal to the voltmeter readings over the ammeter reading. Second, if the resistance of the unknown resistor is very low, that means R is very low. If R is very low, then we will use this circuit to find the resistance of R. The reason is that the voltmeter reading V measures the voltage across R, VR. But the ammeter readings measures the sum of current through R, which is IR, and the current through the voltmeter, IV. That means the ammeter reading will be equal to IR plus IV. Since the internal resistance of the voltmeter is much larger than the resistance of the unknown resistor, which is very small, therefore the current passing through the resistor R will be much larger than the current passing through the voltmeter. As a result, the ammeter reading will be approximately equal to the current passing through the resistor, that is IR. Again, we can use the equation resistance R equal to VR over IR, which is equal to the voltmeter readings over the ammeter reading, to find the resistance of R. Potential divider. In the circuit, we have a battery of EMF E and two resistors of resistance R and R pi. The current in the circuit I equal to E over R plus R pi, and the voltage across XY is equal to the voltage across R pi, which is equal to I times R pi equal to E times the ratio of R pi over R plus R pi. A potential divider is make use of resistors to divide the EMF of a source into difference ratio. If the EMF is equal to 3 volts, find the voltage across XY for different values of R and R pi. For the first set, we have voltage across XY equal to 3 times 5 over 5 plus 5, which is equal to 1.5 volt. For the second, we have V across XY equal to 3 times 20 over 5 plus 20, which is equal to 2.4 volt. For the last one, R is 5 ohms and R pi is 5000 ohm. Then we have V across XY equal to 3 times 5000 over 5 plus 5000, which is approximately equal to 3 volts. From these examples, we see that if we want to have a greater voltage across the resistor, that means if we want to have a greater voltage VR pi, then we should use a greater resistance R pi in the potential divider in order to give a greater voltage across it. In the circuit, since the internal resistance of the ideal voltmeter is infinite, therefore the resistance across XY is equal to R. Therefore, the voltage across XY will be equal to EMF 6 times R over R plus R, which is equal to 6 times 5 kilos over 5 kilo plus 5 kilo, which is equal to 3 volts. Hence, the voltmeter reading will be equal to 3 volts. If the voltmeter is not ideal, but has internal resistance of 5 kilo ohm, then the resistance across XY equal to R times RV over R plus RV, which is 5 times 5 over 5 plus 5 equal to 2.5 kilo ohm. Therefore, the voltage across XY will equal to 6 volt times RXY over R plus RXY equal to 6 times 2.5 over 5 plus 2.5, which is equal to 2 volts. Hence, the voltmeter reading will be equal to 2 volts.